Hello, everybody. My name is Jack Wessel, and my partner is Alexandra Rudy. And together, we're going to be presenting on what happens when the stack and the heap collide in memory. As we learned this past semester, a program's memory has two main sections in which it stores data: the stack, which grows towards smaller memory addresses, and the heap, which grows towards larger memory addresses. When we first learned about this structure, we may not have thought much of the design. However, as hackers, we now realize the danger that's implicit in this way of designing memory. If we could somehow collide the stack with the heap, we could smash the stack by writing to the heap, or we could smash the heap by writing to the stack, both of which are incredibly dangerous, as we saw in our overflow and joy labs. The first publication that researched these kinds of vulnerabilities occurred in 2005 with Gail Delaloux's large memory management vulnerabilities, and was followed in the coming years by various security researchers uncovering vulnerabilities related to stack heap clashes. However, since then, Linux has implemented a section of memory called the guard page that is mapped between the heap and the stack that prevents this kind of attack from occurring. The guard page exists above the top of the stack and below the bottom of the heap. And if the stack pointer reaches this guard page or a write is attempted in this region, the program terminates with a segmentation fault if the stack cannot grow any farther. Researchers at Qualys, however, demonstrated in 2017 that this current implementation of the guard page is insufficient at preventing stack heap clashes. They showed this through an attack that has four major steps: the clash, the run, the jump, and the smash. This four-step attack allowed the researchers to overcome the guard page's defenses by avoiding this region of memory entirely. This allowed them to intersect the stack with the heap and made it possible to smash the stack and/or the heap. Now, I'll introduce the four steps of the attack in depth. The first step is the clash. This step involves growing the stack and optionally the heap in order to have the top of the stack, the guard page, and the bottom of the heap all directly next to each other in memory. Growing the heap can be accomplished by any number of very large allocations of dynamic memory. There are three main ways to grow the stack. One can call a recursive function and force it to recurse very deeply. One can place massive variables on the environment table, or a function can be called with megabytes worth of command line arguments. Once this step has been accomplished, we are ready to begin moving the stack pointer to the top of the stack. Step 2, the run. In this step, we attempt to move the stack pointer up to the top of the stack so that we are ready to jump over the guard page and into the heap. This step is required because the top of the stack is often several kilobytes above the stack pointer due to various actions performed by the kernel that expand the stack. The stack frame can be moved by instantiating very large stack frames, recursive function calls, or by the library call alloc, which allocates memories in a given stack frame. The researchers at Qualys also found that the argv and environment arrays can be used to consume this memory, but this general method only works locally and not using remote exploits. Regardless, after the completion of step 2, we're ready to move the stack pointer into the heap. Step 3, the jump. Step 3 is very similar to the previous step, in that we must move the stack pointer to a higher memory address. This then begs the question, why is this step even necessary? The answer to this lies in the fact that it is imperative that we do not write or access the guard page during this step. Otherwise, our program will terminate. So our allocation in this step has three important requirements. It must start in the heap, it must end in the stack, and it cannot write to the memory regions that encompass the guard page. The researchers at Qualys found a variety of functions that can allocate memory, meeting all three requirements, such as DCI getText, VFPrintf, and getAddressInfo, all of which are included in the GNU library. Regardless of the technique used, once step 3 is successfully completed, we have essentially already hacked the program entirely. Step 4, the smash. In this step, the hacker simply finalizes their attack on the vulnerable binary. The hacker can choose to either write to the stack, which will smash the heap and create possible heap overflows, or the hacker can write to the heap, which will smash the stack and possibly allow the hacker to overwrite the saved instruction pointer, return to libc, or, as the researchers found, it is even possible to brute force ASLR. At this point, the hacker now has control of the program. I will now pass it on to Alex, who will demonstrate how this attack would work.
Hello everyone, I'm going to demo the stack heap clash exploit using a custom binary on Debian 8.5, which is an old version of Debian that's very susceptible to this kind of attacks. So let's look at the code that we're going to be exploiting. Our goal will be to call this function jackpot that is never actually called inside the file. The first thing to notice is that I have custom malloc functions. This is just to get around the fact that GCC separates the heap and the stack with library memory. So we have to simulate a kind of fake heap using mmap that is a few megabytes above the stack. In actual binaries, usually the heap and the stack are next to each other, such as in sudo. So what our program does is it takes as input as an argument of path and opens the folder at that path and reads an integer n and an array of size n that is stored on our fake heap. Then it takes as input an index and a value and changes the value of the array at that index to the given value. So it also checks to make sure that the index is within the array range. The change value function is meant to represent what a function that we would exploit in the normal program would look like, and it's simple. It just allocates some memory, which we might expect most binaries contain a function that would allocate some kind of memory, and then it calls a further function that actually does the modification in the array. So at first glance, this program seems very simple, very safe, and everything is accounted for, like the range, so it shouldn't be exploitable. But actually, it is exploitable by clashing the heap, the fake heap, and the stack. So let's look at the input that we're going to use. I'm only outputting the first few characters. It contains 4 million integers, so it's megabytes in size. This thus gets the heap, the fake heap, very close to the stack, but not actually touching. So I'm going to open the program in GDB to showcase how the exploit works. So I will add a breakpoint at change value and another one at really change value, and run it on the input. Provide it with any values for now, and let's showcase the registers and the mapping. So we can see this is our breakpoint right at change value, which is right after the allocation of the stack array. And we can see that after the allocation, our ESP is at BFE and so on. And however, our stack, this is the stack, ends at BFF and so on. So therefore, due to our allocation, our ESP has actually gone out of the stack, and we can see it's into our fake heap. So therefore, now basically we have full control of our program because the ESP is within our array and we have the option to modify our array. And that's actually exactly what really change value does. So if we continue until we get to really change value, we can see that if we do an xi, our EBP is actually inside the fake heap as well, and therefore we have access to modify the instruction pointer that's right below it. So if we calculate at which index of the array the instruction pointer would be, and the address of the function jackpot that we want to get to, we can actually just jump right into jackpot. So I have already calculated these values, they are right here. So if I run the program on the input and enter the values, we can see that we have successfully called jackpot.
After seeing the 4 stages of the attack in depth, you may be thinking to yourself, okay, well, cool, but each step is incredibly specific. And so a binary must have multiple very specific bugs. So this attack can't really be very useful, right? And while it is very true that many binaries may not be vulnerable to stack heap clashes, the researchers showed that there are a plethora of programs many of which are incredibly important, that are vulnerable to this format of attack. For example, the researchers developed 14 attacks against sudo, a proof of concept that gains control of the instruction pointer in sudo, and many attacks against exim. So while the attack may be very specific, it is still incredibly useful and dangerous. Luckily, it is very possible for us to defend against stack heap clashes. The researchers determined two major ways in which it is possible to protect any binary, provided it has a guard page enabled. First, the researchers proposed that the size of the guard page gets increased to 1 megabyte, which, while it doesn't guarantee protection from stack heap clashes, is incredibly cheap and easy to implement. Then, the researchers offer a very expensive option, in which many binaries, such as those in libraries or ld.so, are recompiled with GCC's fstack check option. This forces the stack pointer to access the guard page if it changes memory location. So while expensive, this option would make it impossible to jump over the guard page, no matter how small it is, provided that this fstack check option is securely implemented. Thank you, everybody.